The last little bit of section 3.4 that I was trying to figure out how to work in is Descartes' rule of signs. So Descartes is one of those famous mathematicians from a long, long time ago, and this is something that he discovered. So say you have a polynomial function, f of x, p of x, whatever. This is just another way to kind of get an idea of how many zeros you have. So not what the actual real zeros are, but how many. Understand when we use the word real zeros, that means that it could be rational or it could also be irrational. It could also even be, well, that's it. It can be those two things, rational or irrational. So this is not talking about any complex zeros, just the rational or irrational. So it's telling us that the number of positive real zeros, so just positive real numbers that are zeros, of the function equals the number of variations in the sign of the non-zero coefficients of f of x, or else equals that number less an even integer. Wow, okay, there's a lot to unpack there, but I hope that it is more straightforward than you think. I'm going to write the word positive real zeros here. And we'll start with that, and then I'll do the second piece of Descartes. So here we are being asked to use Descartes' rule of signs to determine the number of possible positive, negative real zeros. So to find the number of positive real zeros, possible number of positive real zeros, what we're doing is we're taking a look at our function and we're seeing how often the sign changes from term to term, positive to negative. Just how many times does it do that? So notice that we go from positive to negative to positive to positive to negative to negative. So we're just thinking, how many times does it change? So I was just kind of underlining there, but if you want me to do this, positive to negative, positive, positive, negative, negative. Okay, so it's just how many times it changes. So it changes 1, 2, 3 times. So only when it changes from a positive to negative or a negative to positive. So what Descartes' rule of signs is that he figured out a long, long time ago was that for this function, it has either 3 positive real zeros or that number less an even integer. Okay, so understand that an even integer is simply like 2, 4, 6, 8, technically -2, -4, -6. Basically all we do is we subtract 2. 3 minus 2 is 1. Now we're not going to go any further than that because that would send us into the idea of negative real zeros or something, and that doesn't make any sense. It's just how many positive real zeros are possible, either 3 or 1. Notice that this function highest degree is 7. So for this polynomial function, it has a highest degree of 7. And so it could have up to 7 real zeros. It may or may not, but it could. Now, in terms of negative real zeros, you have to do a little bit of work. So the number of possible negative real zeros is equal to the number of variations again, but when you put in f of negative x. So we have to do f of negative x and then count the number of times that it switches. And that will tell us the possible number of negative real zeros. So we plug in negative x, so 3 negative x to the 7th minus 4 negative x to the 4th plus 3 negative x to the 3rd plus 2 negative x squared minus a negative x minus 3. And then let's just simplify that, and then we'll take a look at how often the signs switch. So anything to the negative x to an odd power is going to stay negative, so that'll give us a negative 3x to the 7th. While we have negative x to the 4th, that's positive, so minus 4x to the 4th. Negative x cubed, again, that's an odd, so it's going to be negative and another even because we have a negative x squared. And then we have a plus x minus 3. So now we just take a look and see how often that switches. So we have negative, 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 positive, positive, negative. So only when it switches. So we've only got one switch here and one switch here. That's it. So we either, maybe I'll zeros there, either 2 or, so notice the same thing, equals that number less an even integer. So I'm just going to go down by 2. So 2 or, and then 2 minus 2 is 0. So what we've learned is it could have no real negative zeros, or it could have 2 negative real zeros. Those are the only two options. It could either have 3 positive real zeros or 1 positive real zero. Now, I'm going to show you a graph of this so you can see it, graph. If we graph it, you'll see that it actually has 1 real positive 0. And that is it. That's all it has. So what that means is we have 1 positive real 0 and it actually has no negative real zeros. That means that all the other zeros of this are complex, meaning imaginary. They're not real, they're imaginary. And I'll show you a graph of that so you can see it. All right, so here's just a little Desmos action for you on the problem that we just did, that last problem on section 3.4. So I'm just showing you the graph of it. I just want you to see that even though it's to degree 7, it actually only has 1 real root, which we can see actually occurs at 1, 0. Meaning that x minus 1 would actually be a factor of this. But there are no other real zeros. So Descartes' rule told us that it would either have 3 or 1 positive real zeros. It has 1 positive real zero. And it told us that it would either have 2 or 0 negative real zeros. And it actually has 0 negative real zeros. There's only one place where it crosses the x-axis. There are other zeros. They are just complex zeros, meaning they're going to be imaginary. Not incredibly useful to us if we wanted to graph. Notice as well, I just want to kind of point out to you that we did talk earlier in the chapter about the number of times the function could turn, and that would be the highest degree, which here the degree of the polynomial is 7, minus 1. So in that case, that would be 6. So this function could turn 6 times, but this function up to 6 times, I should say. Notice this function only turns twice. So it comes up, goes down, goes back up. So a lot of the stuff that we learn is kind of giving us just things that we can have in our toolbox. It helps us to look at the function and say, does this function seem right? Does it kind of follow what I know about my possibilities? And putting all those things together can give us a pretty good idea of what the graph looks like, or in some cases, whether what we've done makes sense or seems correct. And that is section 3.4.